Okay, we started talking about the ear the other day, and I just want to go back a couple of slides, just a quick review. Remember, the ear is divided into three parts. The external ear goes down to the tympanic membrane. I have the video otoscope for us set up today, so you can look in. We can look at everybody's ear. This is the middle ear right here. It's the one that has the ossicles in it. It's the one that connects to the nasopharynx. It's the one that makes you want to blow your nose when you dive or when you go up in an airplane and all that stuff. And then we have the inner ear, which is basically what we're going to talk about mostly today. And it's the amazing organ that is really two organs. One is the cochlea here, which is what we hear with, and one of which is this part here called the vestibule and the semicircular canals, which give us vibration sense, gravity sense, so we know which way is down, make us dizzy when we get on the tilt-a-whirl, that sort of thing. And notice we have this nerve over here that goes out of it, which delivers the message to the brain, called the vestibulocochlear nerve, and that's because it goes from the vestibule and it goes from the cochlea, so it has two branches over here. And this is kind of interesting. Notice there's another nerve that happens to just go right past there called the facial nerve. And that whole complex is deeply embedded in the temporal bone. So you don't actually get to see any of this in lab other than in the form of models. Here's that middle ear we talked about. Notice that there's the three bones. Basically what these three bones do is they magnify these little bitty vibrations of the tympanic membrane. And since this one connects to the middle of it, the vibration is bigger when it gets over here to the stapes. And the stapes you see is the third bone, and it connects to this window right behind it called the oval window. And the oval window sends these vibrations into the inner ear. And then when they have exhausted themselves, they come back out and they kind of cancel themselves out at the round window. We'll go over that. And then this is the nice view from the inside of the middle ear of the stapes and the incus and the malleus. This is the tympanic membrane, which you can see through. And there's a light on the other side of it, and the instrument that has got the light is called the otoscope. Yeah. Always on the test on this, the practical exam, I always lay those two scopes out and say, what do you call this? Because nobody can ever remember. The otoscope is made for looking in the ear, and the ophthalmoscope is made for looking in the eye. That was a little hint, by the way. Okay. So the vibrations hit the tympanic membrane, and this is a mechanical receptor thing. So the movement of the airwaves coming in vibrates the tympanic membrane, which then causes the auditory ossicles to vibrate. You've got these two muscles that I guess I've already talked about that stiffen in case of really loud noises to protect your membrane, the tensor tympani and the stapedius muscle. The inner ear. Now let's go to the inner ear, because now that we've passed the vibrations through the middle ear, we're going to pass it to the inner ear, and that's really what we're going to be talking about today. The inner ear is all full of fluid. It's called endolymph. So whereas the other two parts of the ear were full of air, this part is full of fluid called endolymph. And it's all surrounded by bone, as I said. It's called the bony labyrinth, which is just the bone that surrounds this whole complex. And the inside of on the inner layer of that bone is a thing called the membranous labyrinth. So there's a little membrane on the inside of that holds all the fluid in and keeps it nice and sterile and so forth. The inner ear is divided into three parts. One is called the vestibule, which is that kind of opening kind of cavity. And then off of the top end is the semicircular canals. There are three semicircular canals. And then there's the cochlea, which is that shell formation thing that is kind of shaped like a coil. And so here's the overall look of the thing. That round window where the vibrations are brought in is along in here somewhere. And it gets all this fluid in here vibrating. And especially for sound, the sound is transmitted up this little blue line here, up the cochlear duct. And this duct, when it gets to the top, it turns around and comes back down. So that sound waves, which are turned into liquid vibrating, are carried all the way up here, around, 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 and then back down if they're still in existence. And we'll talk about what vibrations go farther than others about this. This thing is called the organ of Corti, C-O-R-T-I, is the name of the sensory organ that's on the inside of that actually does our hearing for us. It has some little hair cells that kind of vibrate as the sound vibrates by. It causes these little hair cells to vibrate, which then that's what our brain interprets as sound. This corner over here is really in two different parts. One is called the vestibule, which contains both the utricle and the saccule in the middle here. And then coming off of that, there are 3 semicircular canals. Now, just so you know, one semicircular canal goes this way, one goes this way, and one goes, which way does the last one go? Oh, this way, right? So it's like the X, Y, Z axis, that they're all at 90 degrees to each other, and they are the ones that are going to interpret motion for us, and I'll talk about them in just a minute. That's kind of a quick overview of the whole thing. The bony labyrinth is this outermost portion of bone. Just inside the bony labyrinth is the membranous labyrinth that forms the lining of things. And then there's these other membranes in here that carry that hold the fluid itself and have these sensory organs in it. In the semicircular canals, these are the things that cause the sensing of the fluid sloshing around. They're called the cristae, and you will see them under the microscope. We have some nice slides of that. The macula also live down here in this vestibule, this whole area here, and then we'll talk about the cochlear duct soon as well. I think the most important thing to know about the semicircular canals is the semicircular canals, because there's 3 of them, and because they're round, they interpret motion of your head, especially rotatory motion. So if you get on the tilt-a-whirl at the carnival, and that thing turns you around like this, and then you do that for 5 minutes, and then you go to get off, and you're walking kind of funny, well, that's because of your semicircular canals. And I always like to think about the semicircular canals as a hula hoop. Now think about this. I've got a hula hoop, it's in my hand, it's going this around my head like this. And I hold that hula hoop up here, and I turn, and the hula hoop turned with me, right? Now, did the fluid inside of the hula hoop turn? Well, it did some, but it didn't turn as much, right? It kind of takes it a while to get moving. And then when you get off the tilt-a-whirl, if you've been turning it like this, the fluid keeps turning, and when you go to get off, that's why you walk so funny, is because it does keep moving, okay? And so you keep getting those sensations until everything calms down.
Dr. Sessions,
yeah.
How does Dramamine work?
It works on your brain to quiet the areas of your brain that receive those messages. Yeah, good question. So, as far as what do you need to know about this stuff, well, here's some facts that you just have to know. You have to know that the vestibule contains both the saccule and the utricle, and it has receptors that provide sensation for both gravity and linear acceleration. Now, I'm sure every one of you at some time in your life has sat in a sports car, and somebody is driving and you're not, and they accelerate the car, and you feel it. You get pushed back against your seat, but even if you didn't feel that, you would feel yourself move forward because this fluid up there is moving around as you accelerate. And acceleration occurs in two ways. It's either acceleration or it's deceleration. So when they put on the brake, you feel the opposite sensation of deceleration. Well, those are picked up by these guys right here. The other thing is gravity. What is the sensation of gravity? Well, the sensation of gravity is which way's up, you know. And I promise you, if we hung you by your feet, even if your eyes were closed, you would know you're upside down. And the reason you would is because of this, okay? So it senses gravity. The semicircular canals are these ones that deal with rotation of the head, and the cochlea, of course, is the sense of hearing. So that's a quick overall view of this whole thing, and those are really important things for you to know. You've got to be able to sort those out. You've got to be able to know that the semicircular canal works for rotation, vestibule works for gravity and acceleration, and so forth. Okay, the inner ear, the entrance into the inner ear is this thing called the round window. Now, I don't know, they say it's round, I've never seen it, but I take their word for it. But basically, it's where the end of the stapes, the stirrup, fits on this round window. So if this is the round window, here's the stapes, and the stapes is vibrating because of the tympanic membrane and the other two ossicles that carried those vibrations to it. It's very thin, it's very membranous, it moves. I just said that wrong.
Yeah, that was backwards.
I said that backwards, that's correct. It's the oval window. Doesn't this look like an oval that hooks to the stapes there that vibrates? So the oval window is the route into the inner ear with these vibrations. The round window is the way out, and all it is a way of dampening the sound so they don't go bouncing back and you don't hear echoes and all that stuff from one single sound. I think I've said that before. Let's move right on along here. Let's talk about equilibrium for a minute. The equilibrium business is picked up by these receptors in the vestibular complex, and they are these receptors are called hair cells. Now, remember, we just did two senses that work on chemoreceptors. Remember, smell and taste work on chemicals reacting with receptors that have chemical receptors on the end of them. And when the right smell comes along, it fires off and tells you that, oh yeah, I just smelled that rose. On the other hand, these are mechanical receptors. So these hair cells literally have little hairs hanging off of them. And when this fluid moves, the little hair cells move. And when the little hairs move, that sends the signal to the brain that, hey, something's vibrating, okay? Let's just roll on through this. Semicircular ducts I kind of think are so interesting because they're continuous with the utricle. They connect into the utricle over there, and each one contains this stuff in it called a thing called a cupula, which is a receptor. It's basically got a bunch of hair cells on it. They're called stereocilia, and they sort of look like long microvilli. And then some of them have a thing called a kinocilium on them, which is this one large cilium. Works better when I show you a picture. This is not the detail I want to show you here, but well, it's pretty good. So as this fluid sloshes around through these semicircular canals, let's just say, it causes movement of this thing right here. And this thing right here, if it's that plane, and the third plane is right here. So these little deals here are really the receptors. for movement of fluid through the semicircular canal. Now the saccule and the macula and the saccule, which are here in this middle part, they also have these receptors. They look a little different. They're called macula. I'm going to show you close-up pictures of them. So this is the kind of receptor that we have in our semicircular canals. This whole thing is full of fluid out here. This cupula kind of sticks up into that flow, and as you turn your head and this fluid flows one way or another, it causes this thing to move back and forth in the flow. This whole upper part here moves back and forth, and it causes these cells here to move back and forth. We call them hair cells. This whole complex here we call the crista. So this might be a little more explanation for you, but let's just say we're rotating our head one way, and as the fluid flows, it causes this thing to move over, and when it does, that mechanical movement sends signals up the nerve to the brain to say, hey, the body is rotating. That makes sense? It's pretty simple, really. Here's a close-up of that receptor thing. It has this one longest kinocilium. It has these smaller stereocilia. I don't know how important all that is. I don't think that's very important. I just think the most important thing is that you know that it's hair cells, and you can call these hairs if you want to, that do the movement that account for the signals that we get from our semicircular canals. The macula, these two guys right here, this one and this one, are really the macula. And what are they going to pick up for us? What sensations are we going to get from them? That's the acceleration and gravity, okay, to know which way's up. Well, they have the same sort of thing. You see these hair cells down here that also are going to move with movement of the fluid. But notice that in addition to this fluid, there's also these little stones in there. These little stones, we call them statoconia or otoliths. And as these things move around, they just make the feelings that much more intense. Okay? I would say, the way I would describe that is if you go back to my hula hoop idea, it's one thing if if your hula hoop is full of water, right, and your receptors are on the wall, the inside wall of the hula hoop, so when you turn, the hula hoop moves more than the water does. But if you want to really make it good, you pour a little sand into your hula hoop. Now you've got some grains of sand in there, and when you now turn, it really stimulates things even more. So that's really the function of these little otoliths, and I'll just leave it at that. How does gravity work? How do we interpret gravity? How do we know which way is up? Even with our eyes closed, we know when our head is tilted back and when it's tilted forward. And the reason for that is that these otoliths move around in the macula and cause the changes like you see right here. They distort the hairs, and that gives you a signal that, hey, my head's in a different position and up is that way and not some other direction. Where do these signals go? Well, the vestibular receptors, oh goodness, I did something very bad there. They send messages up to the vestibular ganglia. Oh, what a creative name, the vestibular ganglia. Get it from the vestibule. And they then from there they get sent on up via the vestibulocochlear nerve to the parts of the brain that interpret hearing. And we've already talked about that. Remember the acoustic area in our brain. Okay. This is just a quick schematic of that same thing. Here, for the equilibrium sensations, comes up through the vestibular branch of the vestibulocochlear nerve, merges up with the cochlear portion to become the vestibulocochlear portion, goes into the vestibular nucleus and sends these messages around to different places. Now, what parts of your brain do you think you'd like to pass that information to? as to whether you're twisting or turning and which way is up and so forth. Well, there's lots of areas that you'd like to send that information to. One is your eye muscles. Because if you're moving, you want to be able to keep focused on one thing. And if you've been on the tilt-a-whirl, and that's one thing I always try to do, is keep focusing on something. Even though it's moving a lot, try to keep focusing so it doesn't really screw up your brain. Some of it goes up to the cerebral cortex, so you can say, so it reaches your level of consciousness, right? And you realize, hey, we're twisting. Nerve 3, nerve 4, nerve 6, those are all eye muscles, right? That move the eye muscles to keep things lined up for you. Here's the accessory nerve, number 11. Remember what that nerve does? Yeah. So it's going to help you hold your head right to kind of control all of this. Some of it's going to go down to your spinal cord to hopefully help you walk, even though things are kind of confusing. And also going to go send messages to your cerebellum, which we know is what really coordinates all of our movements. So that's kind of an interesting system, I think, how it works. Let's talk about eye movements for a minute. We talked about the eyes. We talked about the nerve. It comes out of the back of the eye. We talked about the eye muscles already. Kind of a review here. But one of the things that we do is we always want to not confuse our brain. Now, when I was a kid, we had these little things called roundy rounds. I don't know what everybody else called them, but things that you could get on and they would go around and you'd run and jump on and get it spinning and get it going really fast and try to throw your sister off of it, and all that kind of stuff. But you'd think if you were moving like that all the time that when you looked out, everything would look blurry, right? Because it's constantly moving past you. But it doesn't look blurry. And why is that? Why does it not look blurry when you're on the roundy round? Well, it's because your eye muscles work so quick that even though you're going around, as I go around, I'm focusing on the door, then I focus on that, then I go focus on that, then I focus on that, then I focus on that, as I go right on around. And if you were looking at my eyes while that's happening, you would see my eyes going, moving just a little bit each time so that I'm always focused on something, okay? Now, we do that normally when we're moving, but what about if your eyes are moving and that's not normal? Well, that's called nystagmus. And indeed, this is usually caused by a little damage to your brainstem or your inner ear. And the police understand that. They understand this system of the brain. So when they stop you for DUI, one of the things they will do is they will say, all right, sir, please stand and look straight at me. And you'll look straight at them, and they'll shine a light up towards your eyes, and what they're looking for is nystagmus. Are your eyes blipping and moving back and forth? If they are, it's because of this, and it's because you've damaged your brain with too much alcohol. It's one of the first signs that you can see. And next time you're at a party and you've got a friend who's pretty drunk, just ask them to look straight ahead and go up and look in their eyes, and you'll probably see their eyes moving back and forth. They're trying to cut down this noise, this out of focus noise that's being sent to your brain. That's what nystagmus is. They do a lot more tests than that. The one that's the hardest, I think, as I've watched people get tested, is do this. Is walk. Because if you have any damage and any dysfunction of your cerebellum, you're going to be doing this. And that's all it takes, man. They're hauling you off to the Clinco, and they're going to do a blood test and breath test, and you're going to be out $20,000 probably for a DUI these days. Okay, so that's so much for those two senses, for the utricle, the vestibule, and the semicircular canals. Let's move over and talk about the ear, the part that we hear with, because it certainly is something we use all the time. And so we're going to kind of ignore this part of it, and we're going to talk about this part over here. Once again, you've got this stapes here. They draw it as a nice little thing. It moves back and forth, and it's at the oval window, not at the round window, as I said earlier. So when it does that, it causes this fluid to move, and that fluid goes up and around, and it goes back down. The blue parts that they show in there are the parts where the receptors are that receive this information. Let's move along. So here's what it looks like under the microscope, and we have some really great slides of this over in the lab. Let me give you one piece of forewarning. This slide is the most perfect slide I've ever seen, because 1, 2, 3 of them look really perfect. Most of them look like this. So there's a piece missing on this one. And so you might have to look at 2 slides in order to find one that's perfect like that. Okay? We have nice models of that, but here's the way it works. The fluid goes up through this duct here that connects to the oval window. It's called the tympanic duct. So this vibration of fluid goes up through this, goes around, it goes through this, goes around, goes through this, goes around, goes through that. Get it? And it gets to the top, and then it turns around, and it comes back down through the vestibular duct, which is the top. Okay. As it goes up there and as it vibrates, it causes movement of this thing right here and this thing right here. And those are very nicely called the basilar membrane, which is the base of the organ of Corti, and the vestibular membrane, which is this one up here. So those vibrations cause very tiny movements in these tiny little membranes, and as those tiny little membranes move, it causes these little hair cells that are right here on this basilar membrane to move, and therefore it gets recorded as a sound. Okay, that's the way our brain interprets it. So, let me go one more time here. We've talked about the ossicles. Let's talk about 2 other things. Let's talk about frequency of sound, and let's talk about intensity of sound. The frequency of sound refers to the pitch. Okay? So, low pitch, which is low vibrations, might be a sound like In fact, if you have a decent stereo system at home and you turn the bass up really high, you almost feel like you can count the vibrations, because it you can almost count them. It's so clear and so low. On the other hand, if you speak at a high pitch, the frequencies are very, very fast, up in the thousands per second. When I was a college student, I thought it'd be really cool to go down to this really fancy, boy, it was the best in town, sound shop called Radio Shack. And Radio Shack was really pretty famous for the quality of their speakers and some of their amplifiers. Not so much the amplifiers, but certainly the speakers. And you could buy a stereo system, and it would tell you that the frequencies of this sound system are from 15 times per second. That's really low bass, up to 55,000, which is really, really high. And so you'd say, wow, that must be a good one. And it usually was. And they put those frequencies on the turntables. You know how much sound could you interpret off of the needle? If it was a really high quality needle, it would get low and high, both, and so forth. Anyway, so that's frequency. And frequency is important because it's going to be determined by which part of that cochlear duct is stimulated. I'll go to that in a minute. What about intensity? What is volume? Well, volume is same pitch. I'm not going higher, I'm just getting louder, right? So that's intensity. So the frequency is determined by which part of that system, which part of the spiral interprets that particular sound. The intensity determines how many hair cells are stimulated. In other words, if it's really loud, it's going to stimulate a whole lot of them. If it's not so loud, it's just going to stimulate a few of them. Going more into detail on this little system here that we talked about. This is the part in the middle, the cochlear duct right here. And notice there's all the interpretive cells are down here on the bottom. You see these hair cells. There's this little extra membrane called the tectorial membrane that kind of moves up and down, and it moves over to the top of these cells and can actually touch it and stimulate them additionally as well. So, but this whole thing is based on vibrations, mechanical vibrations of, the tympanic membrane way back there, the ossicles, the round window, and the fluid that's vibrating. Yes?
So, excuse me, so when we damage our hearing, is it when those little hairs break off?
Well, it can be all kinds of things. It can occur at different levels. Your tympanic membrane may quit vibrating if it gets old and scarred and it's had a whole bunch of infections in there. It can be that arthritis sets up between the ossicles. It can be loss of any parts of this.
Say with like a chainsaw.
We'll talk about loud noises in a minute. Yeah, and don't stick yourself in the ear with a chainsaw, if that's what you meant, which you probably won't. Okay, so anyway, these pictures are kind of nice. This is a really good picture. It tells you everything you need to know probably. Notice that there's this basilar membrane here. There's this tectorial membrane here that kind of flops over and is really floppy and can move with the vibrations. You've got the cochlear duct here. You've got the vestibular duct here. This whole thing here, this whole sensory system is called the organ of Corti. Notice that they all send the messages back here to the cochlear branch of the 8th nerve. And as they do, they go through this thing called the spiral ganglion. Well, why is it called the spiral ganglion? Well, it really looks just like what you see there, but because this whole thing is a spiral, right, going up through the curves, then the whole thing is called the spiral ganglion. I think I've said enough about this. You need to look this over. Like I said, we have good models in lab, and we have good microscope slides in lab. Let's talk about pressure waves. Pressure waves are sine waves. You remember that from your trigonometry, right? How many of you have even taken trigonometry? Anybody have that? I always thought trig was so cool, but wasn't that cool? Wasn't that cool? I thought it was really cool.